we students at the University of Arizona have been hard at work on new ambitions, new visions, and new innovations. Hey, I'm Max, an applied physics student at the University of Arizona. Do you like that establishing shot? That was pretty cool, right? Well, I have something cooler to show you. For that, meet the team. We're Team 46, and we're presenting to you our fiber coupled package test station. Our sponsor was testing their lasers manually, which took considerable amounts of time from their employees. As such, they wanted a station to handle all of the testing automatically, with the ability to modify their tests as needed. Our solution is a station where an operator can place a fiber and run all selected tests safely and accurately. Our minimum viable product is a station with all the required measuring devices able to move in and out of the optical axis. Due to time constraints, we were unable to get a laser driver or machine aperture before design day. Our sponsor will complete the remaining tests that we've outlined. Some things we must go over before we get started. First, the two cameras that we have monitoring and measuring in our station. One measures the field pattern of the laser, and the other ensures proper alignment of the fiber within our station. This is the thermopile, which essentially measures the power of the laser. This here is the aperture. It blocks as much cladding light as it can coming from the fiber's cladding. It works in conjunction with the thermopile to measure the fraction of power held within the cladding light.
The screen functions as a beam dump and is used to see the field pattern of the laser. Finally, we have two computers that collect and analyze the data received. The Programmable Logic Controller, or PLC, automates almost every aspect of the project. It is used to get instant data and monitor the system, although it cannot read USB and Ethernet signals, which is why we have the PC. The PC receives the rest of the information from, but cannot interact with data as quickly as the PLC. The PC supervises and moderates all of the data.
Sorry about that. Now I can move on to the process. Before any operation, the station allows the operator to determine which tests will be made and modify them as they desire. They also have the option to do a full characterization test if they choose to do so. First, open up the machine and put the laser diode into the carrier. Electrical power will be pumped into the diode, which then allows the diode to produce the laser. Step 2, place the fiber into the fiber holder. Once done, close the machine and press start. Step 3, ensure the Logitech 4K camera is aimed at the fiber and make sure it's aligned properly. On step 4, the laser is activated and is incident onto the screen. And the off-axis camera is looking at the field pattern of the laser for data. The camera ensures proper alignment and reports any potential problems to the operator through the PC. Once data is analyzed by the PC, the laser is then turned off. Step 5, the thermopile slides in and the laser is reactivated. The thermopile collects data that gets sent directly to the PC. The spectrometer is used on the side to determine the light's wavelength. After that, the laser gets deactivated. Step 6, the aperture slides in and the laser turns back on. That way, the beam will go through the aperture and hit the thermopile. Step 7, the laser turns off and both the aperture and the thermopile are pulled back to their original position. The station checks with the operator for pass or fail data depending on given intervals for characteristics like power or wavelength. Yeah, that's what we're making. Question. I have a question. What would you do in the event if something starts burning or melting? Well,
I'm glad you asked. We have cooling water systems across the laser aperture, screen, and thermopile. The way it works is that the water goes back into the house water supply to continue the flow of water. That way the water is continuous and the laser is cooled. The PLC and PC detect anything bad happening, or the product detects a leak in the water and it will alert the operator. The other precaution is a big red button that immediately stops the process.
From the information we've gathered,
the PC and PLC are in constant communication through Modbus TCP. The operator interfaces with the PC, which analyzes all the incoming measurements and lets the PLC continue to the next test. The PLC ensures automation and safety throughout the experiment. It controls all the movements other than the piezomotor stage and measures power and temperature.
We were given a budget of $4,500 by the U of A. Due to the sensitive nature and precision of the equipment that we used, we've exceeded that by a little bit. Anything above that was provided by our sponsor. We've taken into account for the cost, the structure, the alignment of the pneumatics, the thermopile, the screen, the camera, the power, the hardware, the cooling and mount for the laser, and this totaled to $25,000 and $540. This project was an incredible opportunity. For me, I learned how to lead a team and how to work with PLCs and controls engineering.
Yeah, I was in the news as well. I learned how to talk to railroad companies, procurement process, what goes into that, and a lot about the core fundamentals of starting an engineering project.
I got to learn about engineering drawings and working as a team.
As a systems engineer, it was really fun to finally get my hands on some proper hardware and really get to play around with stuff.
Thanks for joining us and watching the video. I'd like to take some time to give thanks to the University of Arizona for making this possible, and especially to our sponsor, Leonardo, and everyone who helped in the making of this.